Hello everyone, I'm Mathis Vulliez. I'm in my fourth year in ECAM Lyon in an engineering program. I'm here in front of you to present you my applied internship oral. So the title is The Measurements of Acoustic Absorption by Synthetic Antenna of Sources and Microphones Doublets. It was a 3-month internship, which starts in 30th of May and it ends on the 26th of August. 2022. So I'm going to do a little summary. So it is divided in 3 chapters. So first, a brief presentation of the host company. Second chapter is the presentation of the project, and for the chapter 3, it's my work as an internship, as an intern, sorry, divided in 3 parts. Then a conclusion and the bibliography. Sorry for my kids. So first, a brief history of the Ghost. So the Ghost is my host company. It's a research laboratory, which was created in 1984 by Sir Jean-Nicolas. It is in Quebec, in Sherbrooke, so at 1.32 hours from Montreal. And in charge of the Ghost, there are 7 teachers. So my supervisor was Alain Berry and Olivier Robin. This research laboratory works with like more than 50 students, postdoc, PhD students, etc. And there are 6 expertise: vibroacoustic, acoustic materials, active control, imaging, ultrasound, and sound quality. And I was more in acoustic materials. I will present you briefly the main projects that I worked on. So my project was with the University of Sherbrooke and the Ghost Laboratory, IRSST, sorry, and ETS, so the École Technologique Supérieure de Montréal. Those 3 entities works on the same project. The main entities is here IRSST, who works on the research to reduce the accident on the work for operators. So they all work in 4 different ways to reduce the acoustic accident. And my project was to increase the coefficient absorption. So you have several ways to reduce the accidents. One way is to characterize materials and to characterize them by their coefficient of absorption. That's what I worked on. My first part of my work was to study the limits of the standardized methods, because to have the coefficient of absorption, you have several methods, and there are new ones and very old ones. I worked with the ASTM International, so it's the standardized method. It's all we can find to have the most reliable measurements, and that's the next part. So I worked on the reverbation room method, so it's C 423.22. So basically, I have to make to find the coefficient of the absorption of 3 different materials using the reverbation room methods. So the main goal of this room is to create a diffuse flux. So what is a diffuse flux? It means that wherever you are in the room, you will have the same propagation of sound in the space. Respecting the standardized method, you have to have 5 microphones. So they are here in red, 1 sources, and at the middle of your room, you have to put specimen materials to test. These materials should have an area superior than 6.68 meters squares. Also, in order to have only the upper part of your materials, we created a wooden frame in order to not have the absorption of the surface, but only the upper one. With this, you have to get two reverberation time. So what is a reverberation time? It's the time that makes the sound to have a decay of 60 decibel. So you create two reverberation time, sorry. One with your room when she is empty, so like this, and one with the materials. With this equation, with the speed of sound in the air, the volume of your room, and I don't remember which is. I didn't read, so sorry for this. Surface, that's the surface, yes. Thank you. With the surface and your two reverberation time, you can have the coefficient of absorption. That's what we want. So I told you that we make this for 3 different materials. So rock wool, glass wool, and recycled cotton. And what we can see is that your coefficient of absorption should be between 0 and 1 because it's physics. And what we can see is for the two alpha rock wool and alpha glass wool, it's above. So it's not working. It's not physically correct. So we cannot send something that it's not physically correct. So that's why this standardized method is not working at all, and we should have another way. This other way is the goal of the project. It's a new way to characterize materials. This new way, she's here. So at CRASH-UdeS in Montreal, they created SDC. So it's I will talk only of SDC. SDC is the benchmark. It's for synthèse de chant, so file synthesis. So when I will talk about this, it means the benchmark here. So basically, what you have, you have your materials, you have microphone doublets, and you have sources. You have a mesh of sources on the above the materials, and what you will do completely with a rigid surface and free field, like in anechoic rooms where you have free fields, so no reverberation. With this mesh, you will get the transverse function between those two mics, and between those two mics, you will be able, thanks to an inversion of the LR model, you will find the property of the materials. So it's anyway, this aspect of the project was not for me. I was more on other part, like to study the limit of this project, and yes. So what we can see is that thanks to this method, we can get an absorption coefficient. So in red, you have the measurement made with SDC. And in blue, it's the reverberation rooms. So we can see that for the same materials and two different methods, you have not at all the same results. And what we can see, it's for SDC, it's much more reliable because you don't go above the 1 limits. But what we can see is that in low frequency, it's not really clean. And it's a little bit a problem for us because it's in low frequency that it's very important for us to understand how the materials will act and what are those characteristics. So we have several hypotheses concerning those peaks and those gaps here, and I studied on them. That's the second part of my work. So with different software like Creo 6.0, COMSOL, Multiphysics, and MATLAB, I had to study two different hypotheses. The first hypothesis was that this gap was due to the effect of the size of the materials, because in the LR model, you have an infinite size. You don't have a finite size. But on the ATS, you have a finite size. So maybe those gaps are due to the diffraction effect of the border. And also, I have to study the impact of the structure of SDC on the measurements. So, for the first part, first at all, I told you that we were in an anechoic room, so I have to recreate a free field. So for this, in COMSOL, you have what it's called perfectly matched layer, so PML. And I have to test that my PML in COMSOL was working correctly. So what I did, it's I recreated in MATLAB what I should obtain with a free field. So I put a real source, a symmetrical source, my rigid surface, and my microphone doublets. With this, I recreated my free field condition with a rigid surface, sorry, and a free field. Then I just got P1 and P2. I obtained the transfer function. So with all those data and the different dimensions. And then I recreated it on COMSOL. So on COMSOL, I have my PML, so perfectly matched layer. So I should have not, I should obtain no reverbation at all. And this is a mesh. And this is what I obtained. So in blue, it's the data coming from my MATLAB model. So the theoric value for the module and the phase of my transfer function. First, I had this, sorry, and it was not clean. So the answer was to have the correct mesh because my mesh was too big for the frequency I had. So with a better mesh, I have these results. And so I can conclude that my PML is working. So my PML is working. It means that I have reliable references and I can study the two hypotheses. So the variation of the size of the materials and the impact of the structure of SDC. Sorry. First, I have to present you the mesh that are for me my reference. So it's the mesh of sources of the SDC project. So when I talked about the 25 sources, it's this one at the middle. And I will also use the 22 ones. And you can see that this triangle of sources is recreated here on my COMSOL project. It's just to be on the same wavelength. So this is the result. So this is the comparison of the size of the materials. So I start from 0.6 and 0.6 meters to 2.2 meters. One important fact that this dimension here is the real dimension of the materials that ETS at Montreal used. So that's the reference one. And we can see so those gaps, again, from the black curve. The black curve is the SDC measure. And all the other colors are my difference simulation. But okay, so there is a zoom. And so we can see that when your materials is bigger, like 2.2 meters, the blue one, it seems to reach, no, it's not really that, but it seems more on the measures, the black curve coming from SDC. But it's not very relevant. So I tried to do the same experiment, but on smaller materials. So again, the green curve is the reference ones. SDC is a measure coming from ATS. And what we can see is that it's really clean, but when you are in a very little materials, with a very little materials, it's not reliable at all. So again, the module and the phase. So we we can see that there is no. Oh yes, I forget, but we can see that you do not sorry have the same gap in the simulation than in the measure. So we can say that the diffraction effect due of the size it's not just is not the answer. But we can see that there is a limit value for the model COMSOL of 0.2 by 0.2. So the other hypothesis was the impact of the structure of SDC. So thanks to Creo, I created the same SDC benchmark, this one in Vulliez, and I imported it in my COMSOL model. And the goal was to identify maybe which of the structure of my benchmark could create those entities on the low frequency. We first thought that it was the microphones, the source support here. So I tried by moving him and removed it to find what to see what can be the results. So these are the results. So again, we are in position 25, so at the middle of my materials. You can see those gaps that we are studying. And so in red, you have the simulation without the SDC benchmark. In blue, you have the simulation without the sources support. And in green, you have all the benchmark. And again, in black, you have the measures. And so we can see that for the module, you can find the same deformations. I will show you for the phase. So again, you can find the same things. And in position 22, so it was very interesting because you are at the extremity of the materials. So you can have it is where you can find the bigger effect. So you see here for the low frequency. But again, what we can see is that the SDC support, the benchmark, seems to have an impact on the results, but it is not the same at all as the measure coming from SDC. So that's the part of the last part of my jobs, to identify this structure of the SDC to find which one could create this. But I'm currently today I'm doing auto test, so it's not finished. Like it can be involved. Get involved. Sorry. So the SDC seems to have a real impact on the measurements, but the peak in low frequency are not explained yet, and maybe there will be new hypotheses for this. Since I'm going to go back to France and I will not able to work on this project again, I had to create the digital twin of the experiment by created the French guide of my COMSOL simulation for the project. So tomorrow, if someone is on the project, he will have everything that I did, how to move things, to recreate, to change parameters. So that's the end of my internships to write the COMSOL grade. So to conclude, I like to say that that's my first time in the acoustic field. In Lyon, I was doing energy and environment. And it was for me the best opportunity because I really loved this internship. I really loved all the skills that I've learned. I really loved all the person that I worked on with who helped me a lot. I would like to thank Alain Berry and Olivier Robin, who were very great and kind with me. during all my internship. And that's my bibliography, and I would like to thank you for your attention.